let's start up again. Last round for another hour. Dan, thanks for doing this.
Okay. So, picking up where we left off. So we spent the last hour introducing this representation of mags and pags, talking about FCI as a constraint-based approach, very similar to PC in its like underlying logic for learning in the space of mags and pags, and showed how it could work in some really simple examples of just a few variables. One thing I wanted to, so there is, as I sort of mentioned earlier, there's all this theoretical machinery for what you can do with an ADMG if you have one in the general class of ADMGs, like the identification algorithm, the ID algorithm, or identification results for various kinds of causal effects and so forth. So I want to spend just a little bit of time mentioning some stuff you can do with a mag or pag if you have one, because it's not quite the same thing. So obviously, the mag or pag will represent to you in a qualitative way ancestral relationships and some stuff about confounding, right? So there's a kind of qualitative conclusion that you can read off the graph. One important kind of property that I alluded to earlier is this fact that some directed edges can kind of hide or be ambiguous between the existence of only an ancestral relationship or both an ancestral relationship with unmeasured confounding. And there's a criterion that you can use thinking about visible and invisible edges, which distinguish between the two options. So in particular, if I have a mag or a pag, it's the same for both, call it P, and I have a directed edge in that graph from X to Y. We call it visible if there exists a vertex Z not adjacent to Y, such that there's an edge between Z and X that is into X, meaning has an arrowhead in X, or there is a collider path between Z and X that is into X, and every non-endpoint vertex on the path is a parent of Y. Otherwise, that edge is called invisible. So what does that mean? It's kind of hard to parse, but what does that mean? It says that I'm interested in this edge between X and Y. And so the first part of that definition says, if there is an edge between Z and X that is into X, so I'm going to let this be kind of any endpoint I want here, that is into X, and it's got to be non-adjacent to Y. And so that's the first part, or it could be a bit more complicated, and you could actually have a Z that has a collider path. So it's not necessarily directly connected to X, but connected by a bunch of colliders into X, such that every non-endpoint vertex on that path is a parent of Y, for example, like this kind of thing. So either of these could hold. And if that's the case, then this edge, directed edge between X and Y is called visible. So ignoring the second part, the first part is kind of enacting this Y structure thing that we saw previously. It's sort of basically saying that if there's an edge that looks like this from Z to X, and there is no adjacency here, it's going to lead to a kind of conditional independence between Z and Y given X, which means it's sort of incompatible with a unmeasured confounder between L and Y. So visible edges sort of are ones that tell you for sure there is no unmeasured confounding between X and Y, or the graph is incompatible with unmeasured confounding between X and Y. Whereas if they're invisible, you don't know. And so and the kind of more complicated clause is a generalization of this logic. It basically says that if there exists this kind of pathway, then the d-separation relations would change whether there's an L there or not. So if there was this kind of pathway, then there would be a non-adjacency between Z and Y, then there must be a separation between them. so that it's incompatible with an unmeasured confounder. So that's a kind of neat, I never really think about it this way. I kind of just think about it as this kind of thing. It's kind of a neat thing that you can algorithmically read off of a graph. Like you can just ask your computer program to implement this definition, and you could sort of like highlight the directed edges that are visible and are ones that are sort of, you're sure that there's no confounding there. So that's kind of nice. So it's not, so I kind of gave mags a hard time earlier because they're less informative than a regular ADMG, but they're not totally uninformative. There are things you can learn about unmeasured confounding, even if there's no bidirected edge appearing there. Okay, and so that's why when we saw that example with the Y structure in the little R code, there was a directed edge, Z1 and Z2. There was a directed edge between X and Y in the case where there was no actual unmeasured confounding between X and Y, right? When I generated the data such that the L had no effect on X, right? And then as soon as I put that edge in there, I no longer stuff became undirected, and I sort of induced edges between Z's and Y's. Make sense? So, yes?
There's an interesting question on Zoom that maybe you could say something about. Is there a GES type algorithm? So I guess a score-based type of algorithm for mags?
Good question. So the question is if there's a score-based algorithm for mags and pags. I'm sure I'm going to get to this a little bit later. The answer is basically no. I mean, there are hybrid procedures that use some score-based concepts that try and learn mags and pags, but there's no strictly speaking GES for mags and pags. Part of the reason being that the problem of search, so in the case of GES, you're searching through the space of CP DAGs by adding and removing undirected edges. And there are some nice theoretical results that tell you how to do that correctly and that figure in the proof of its consistency. If I tried to do the same thing for mags and pags, I have many more options, right? Because I could add or remove directed edges or bidirected edges. Or if I allow for circles, then all of these combinations of things. And so there isn't really a fully formed greedy equivalence search procedure for mags and pags. There are score-based things that are somewhat useful for mags and pags. I'll get to more recent work at the end of this slideshow. But as a quick example that I won't mention otherwise is there's a kind of hybrid GES and FCI algorithm called GFCI, greedy fast causal inference, which basically uses greedy equivalence search as like the first step and then unorients things and then does FCI on top. And that can be useful just in the sense that it's faster because you can use GES and it can scale it up nicely, and it can be more accurate and stable in small sample sizes, but it's not really a full greedy procedure. Yes.
So is the problem here that it's difficult computationally for a score-based approach, or is it that there aren't good scores for mags?
It's neither really. It's that there's not really good theory for how to do the score-based search. Like, in order to traverse the space of PAGs, you need to prove some stuff about edge additions and deletions to a starting graph and prove that the way that you do it won't get you stuck in a local optimum. And so that theoretical result doesn't exist. I skipped over it in my previous slides, but I had a slide about Meek's conjecture, which is a kind of theoretical property for DAGs. That was not, it's not a conjecture, it's a theorem now. And just there's no Meek's conjecture for mags and pags as of yet.
But you can still score a mag using.
You can score a mag, yes. You can score.
Brute force thing, right?
Right. If you wanted to do a brute force thing, you can calculate scores for mags. You can calculate likelihoods for mags. I'll mention that a little bit later. But yes. Yeah.
Thomas, do you want to comment on this?
Yeah, I just wanted to add a very quick comment there. So yeah, so you can compute BIC scores for mags, both for discrete data and for Gaussian data. And so yes, I think it's important to say that the thing which is lacking is a proof of consistency or of some score-based search. But you know, in reality, we don't know that that's a theoretical property. It doesn't tell us within any given time when you run GES on real data that you're getting the maximum. So yeah.
Right. So yeah, so there are theoretical proofs for GES that tell you in the limit of infinite sample size, you shouldn't get stuck in local optima. And those things are even lacking for MAGs and PAGs. But if you want something stronger than that, for finite samples would require more work. Yeah. So I should say, I will talk a little bit about kind of more, all the methods I'm been talking about today are at least 20 years old. And I'll talk a little bit about some that are a bit more recent towards the end here. So, so just to conclude this little bit, the definition of visible edges can be useful for reading off information about confounding in the MAG or PAG that you might learn. There's also a backdoor criterion for MAGs and PAGs. So in the case of DAGs, we know that one way to estimate some sort of causal effect or post-intervention distribution is to do backdoor adjustment. So adjust for a certain set of covariates that satisfies Pearl's backdoor criterion. That kind of criterion has been extended to MAGs and PAGs. I'm not actually going to go through this. I'll just leave the slides for you to look into if you're interested. But there is a backdoor criterion for MAGs and PAGs in the sense that if you're given a PAG or a MAG that you've learned from FCI, you can define a certain set. What is it here? It's called DSEP XY is defined here. And you can check a certain graphical criterion, which involves removing edges from a certain subgraph of the original graph and checking whether descendants intersect with certain other sets. I won't go into it, but if you satisfy this criterion, then this set DSEP that is calculable from the graph is a sufficient backdoor adjustment set. So it means that if this criterion is met, I can estimate the causal effect by adjusting for that backdoor set in the MAG or PAG. And but there's a lot of and actually I should mention that there's a do calculus for MAGs and PAGs, which is in the paper I cited earlier by Jiji Zhang in JMLR from 2008. But it doesn't have quite all the nice properties that do calculus has for general ADMGs. At least the version Gigi did is not complete, but then there's some more recent work by Barenboim and co-authors that adds to that as well. So this is all a way of saying that there's stuff you can do with a given MAG or PAG if you're interested in stuff like backdoor adjustment or do calculus, but it's not quite as easy or well developed or complete as the theory for ADMGs in general. And here's my list of references for all these papers that I've mentioned. This first paper proves and characterizes Markov equivalence for ancestral graphs. Actually, this paper by Thomas and Peter from 2002 is the one that introduces ancestral graphs. A little bit of kind of very brief history, and Thomas can correct me if I'm wrong, but the FCI algorithm was actually first presented in some papers in the late 90s with Peter and Thomas and Chris Meek. Usually the citation for FCI is in the book by Peter Spurdes et al. From 2000. But a kind of confusing thing is that the original formulation of FCI was formulated without MAGs and PAGs, really. It was formulated with a different kind of graphical representation called partially oriented inducing path graphs, which I think is maybe the funniest acronym in causal discovery, like POIPGs, or I don't know how you're supposed to pronounce that. So the original, if you go to this book, it'll tell you FCI, and the output won't look like the output that we've just discussed here. And it was reformulated to be represented in terms of MAGs and PAGs only later than that, starting with these papers by that reference ancestral graph models, Markov equivalence, and in particular this paper by Jiji Zhang on the completeness of FCI when you interpret it in terms of MAGs and PAGs and so forth. And then the backdoor criterion stuff I just mentioned is in this paper by Mailus Matuis and Diego Colombo, and then another paper that sort of generalizes FCI or makes FCI more feasible in high dimensional settings with some computational changes. So if you want to dive into the literature, on FCI and MAGs and PAGs, this is pretty much a good place to look. Okay, so I'm going to conclude the sort of FCI, MAGs, and PAG stuff here and talk a little bit about alternative approaches to causal discovery that are not really necessarily direct descendants of PC and GES. So, so everything that I've discussed so far today has placed, at least in principle, no real assumptions on the causal graphical model, except that it's generated from a DAG, right? They've been kind of non-parametric as possible. They haven't said anything about structural equation models. They've assumed that there's data or there's a distribution that's generated from a DAG. Maybe it's a DAG with unmeasured variables, and that distribution has to satisfy faithfulness with respect to the graph, and then various machinery works through. But an alternative approach has been to place some assumptions on, for example, the structural equation models that you're willing to assume lie behind the data generating process, and to try and learn something based on those assumptions.
Can you just stop there?
Yes.
Yes, sorry to jump in. I was just trying to get back on the previous point. So just one thing I wanted to highlight, a paper that Emma Pokovich also did work on backdoor criterion and sort of tied up the final loose ends on complete graphical characterization and construction of adjustment sets for MAGs and PAGs. And I was also going to say, just briefly, the FCI algorithm is actually in Peter's book from 1993. So the original version is in there. And the output is pretty much the same as you get viewing it as a PAG or as a Poitry, as you described it. The only difference is you get a couple more orientations. There are certain circles that get replaced if you view it as a PAG. But yeah, although those also create issues for people trying to do backdoor adjustment. So anyway, that was just a complete, you asked me to correct anything, so I'm just adding it in here. Sorry.
Yeah, thank you. Yeah, and Emma's paper on backdoor adjustment is one that I probably should have included up there as well. So thanks. Okay, so moving on. So the kind of non-parametric structural equation framework is one in which every variable is assumed to be some function unspecified of its parents in the graph with some error term, right? So this is super general in the sense that it places no restrictions at all on the observed data, and is a kind of very weak set of assumptions. And then people start making independence assumptions about the errors and so forth on top of these things. But a kind of popular class of structural equation models that is much more restrictive or makes a much stronger set of assumptions would be linear models. So in a linear model, it's like a special case where these Fs are just linear functions, linear combinations of the parents. So the kind of interesting thing about making somewhat parametric or semi-parametric assumptions about the functional forms is that these can induce a certain amount of asymmetry on the data that can be helpful for causal discovery. So linear models are popular, they're convenient to analyze and estimate. They're very obviously not universally applicable because there's lots of examples of things that are exhibit nonlinearities. But if you do assume linearity, and in addition assume something about the distribution of the error terms, in particular, it's been shown that if you are willing to assume that the epsilons, these errors, are non-Gaussian, are independent but non-Gaussian, then that is sort of is provably enough to induce a kind of asymmetry on the observed data joint distribution, which can help you identify a unique DAG instead of a Markov equivalence class. And as a kind of long footnote here, it's not really common outside of causal discovery very much to think about linear structural equations with non-Gaussian errors. Obviously, Gaussian errors are very common in a lot of areas of statistics and econometrics. But linearity and non-Gaussianity of the errors can coexist, and this will induce non-Gaussianity on the joint distribution over the x's, right? So the kind of correspondence is that, like, if you had Gaussian errors and linear functions, that induces a Gaussian joint distribution. If I know that I have a Gaussian joint distribution, then I know I have linear functions. But if I have linear functions that are non-Gaussian, then that'll introduce a non-Gaussian joint distribution over the x's. And so in this case, this would be a model in which the epsilons are unspecified, but not Gaussian. And a kind of interesting observation, this is from a paper by Hoyer et al. From 2008, is that that kind of non-Gaussianity in the context of linear models induces these asymmetries, which you can observe in the residuals from fitting those regressions. And specifically, just thinking about two variables, which we talked about earlier as being kind of this impossible case. Non-parametrically, if I have two variables, these different structures all induce the same dependent structure between x1 and x2, namely there is no independence, but can induce different constraints on the covariances or on the error residuals. So as an example, if I think of x1 and x2, and then E1 and E2 are the errors, then model 2 is one in which x1 causes x2. And so there's some coefficient alpha in the linear structural equation model. Model 3 is one in which the direction is reversed. So there's an alpha from x2 to x1. And you can, for each one of these cases, write down what is the induced variance and covariance over the x's, and see that if things were Gaussian, then the covariance matrix, the covariance has this kind of symmetric quality to it, right? Like that there's no way of distinguishing whether going in one direction or the other just based on this covariance matrix in the case where things are Gaussian. But in the case where things are non-Gaussian, the residuals will sort of have different orientations depending on which direction the influence goes. So like a kind of an example, I think this kind of simulation example, the last column is one in which the noises are assumed to be uniform instead of Gaussian. So that's an example of a non-Gaussian distribution, whereas the penultimate column is one in which the noises are Gaussian. So for all of these cases in the Gaussian setting, all you can conclude from those residuals is that there's an association between x1 and x2, right? A kind of linear association in particular between x1 and x2. But when you start allowing for uniform noise, you can see that the residuals exhibit this kind of asymmetry based on the thresholding, right? So like the walls of the residuals correspond to like the direction of uniformity in the first error, and then there's that's propagated to the second dimension. And so this kind of principle, this principle of allowing for or assuming a particular functional form for the structural equations and something asymmetric about the error distributions can be used to distinguish between possible candidates, even just in two variables, and even sometimes in the case with unmeasured confounding. So as an example, the kind of one algorithm that exploits this kind of approach is ICA LIGAM. So LIGAM is the kind of general term for linear non-Gaussian acyclic model. And there's a lot of kind of different algorithms for learning LIGAM models. And the kind of classic one is based on independent components analysis. So I'll describe really briefly how it works and then talk about the version that allows for unmeasured variables. So say I assume there's no latent variables first to explain. In that case, you can show that if a LIGAM model holds, then the algorithm may identify a unique DAG rather than equivalence class. And I'm sort of caught in the paper, a review paper by Shohei Shimizu is down here in the footnotes. And the kind of, but like a fundamental thing to keep in mind here is that you're drawing stronger conclusions than you would if you were using PC, right? You might learn a unique DAG instead of an equivalence class, but you're also making stronger assumptions, which may be defeasible, that there is this linear non-Gaussian model underlying your data. So the way that LIGAM kind of very roughly works is that I can describe the linear structural equation in matrix form as above. So like x is just b times x for some matrix of coefficients. Oh, sorry, question here?
Just a question about the Nongaussianity result. It's about the dependence. That happens, for example, if I have the copia that are non-Gaussian, but the marginal are Gaussian. Well, how it's about the dependence or it's about the joint distribution?
It's about the joint distribution of the errors.
Of the error.
So if you have, I guess if you have if the joint distribution of the epsilons is in the Gaussian copular family, I guess so long as it doesn't reduce to Gaussian for each one, then it's non-Gaussian.
I see. So the result is well, if the joint is a joint distribution that need to not be Gaussian. So for example, if I have a Gaussian copular and that the marginal are non-Gaussian, the result will not work.
The Gaussian copular and the marginal. If the marginals are non-Gaussian, the result will work. Yeah. So you can have, I think the result for ICA LIGAM is you can only have at most one Gaussian error out of all of them. And so as long as each of the rest are non-Gaussian. So it kind of depends, like a Gaussian coupler includes Gaussians, right? So you have to like exclude that bit.
I see. Because in the example that you show, it was about the dependence, because the correlation that you show, it's just this comparison, just for the dependence that has like the Gaussian structure. So it's just more about the market, something that was involved in the market.
Yeah, I mean, I guess the way that I would put it is that ultimately what it's going to do is induce some sort of induce something about the covariance between the x's, right? Which is about the dependence between the x's. But if you have, it's like how many degrees of freedom there are in this ultimate covariance matrix at the end. So I think it's just individual errors as long as you know more than one of them. Well, at least some of them are non-Gaussian, you'll have this asymmetry. Yes.
I'm curious why no one asked it, but I will ask it. What is the precise notion of non-Gaussianity? Means that we are total variation distance is epsilon far from Gaussian. Means that I can find an enormous number of ways to describe the non-Gaussian. So, what is your interpretation?
Well, there's going to be more than one way that is equivalent. I think a lot of the results in like the LIGAM literature are kind of based on the existence of higher moments. Right? So for Gaussians, it'll just there's only the second moment and that's it. And so as long as you have non-zero higher moments, you can induce some asymmetry. But it kind of depends a bit on which paper and which algorithm you're talking about. I think that's the way that it's proved for this stuff.
Wait, comment one. Gaussian has higher moments in the even cases, I think.
Non-zero, Gaussian just has mean and variance, right? So you have to have some non-vanishing skew or kurtosis or whatever.
Value of x fourth equals
No, zero.
Gaussian. Is a variance of.
It's completely determined by mean and variance.
Yeah, no, I agree. Like, I'm saying something different statistically, but anyway.
Maybe we can talk about it offline. Yeah. So another question here?
So it's a bit related to what you said. What if the non-Gaussian distribution is something like Cauchy? Because in the picture that you showed, it's very obvious that they're different because you have finite support. But what if you also have infinite support and it's also symmetric like Cauchy distribution? Does it still work?
It does, yeah. I don't know if I've ever seen that as an example in the stuff, but I think
That's what you said as well. It's about the higher order moments, and because you have higher order moments.
I see. So it's not so much about not being Gaussian, but having higher order moments.
it's not about not being symmetric, it's about not being just.
Right. So you might need a lot of data to do the inference, whereas in the uniform group, so it'd be easier. But the Cauchy would be just fine.
Well, you might run into other problems because your moments might be diverged. It depends how high you have to go. So it might be a different problem you'd run into. So I expecting you want this thing to have moments of all orders.
And there's a difference between what problems you run into practically speaking in this setting versus what you can prove about identifiability. So I think the identifiability, like usually, like for these papers, typically they'll prove that under such and such assumptions about the errors and structural equations, there is a difference in the drug distribution going one direction versus another. And so I think as long as you have higher moments that are non-zero, you can show that there's a difference in those distributions. Then how you actually estimate those things with a particular algorithm is kind of a separate story. And so usually they use, one of the basic approaches is using independent components analysis, which I'll describe here. And that kind of depends on, estimating some matrix such that residuals look independent. And that can be easier or harder to do depending on what particular way you use to solve this problem. So really quick, I just want to say that, I started off by saying that here's the linear model in matrix form. And then here's the same model, just turning A into the identity matrix minus B with the inverse. And so in this model, we will say that if there's a coefficient, then there's a corresponding edge in the underlying DAG. And so kind of what you want to learn the DAG is those set of coefficients. ICA, independent components analysis, will typically focus on estimating the inverse of this A matrix. Specifically, the algorithm will find an estimated W, the inverse of A, such that the resulting residuals look mutually independent, right? Which is the underlying assumption of the linear model, at least in the case without latent variables. And the way it'll do that sort of depends on the details, but it's usually based on minimizing this kind of mutual information metric between the vector of error residuals. It usually requires some model for estimating those mutual information pieces and so forth. But that's what ICA LIGAM basically does. But a caveat to all this is that ICA will only estimate that matrix W hat up to a permutation of the columns and a scaling factor. And so there's going to be some additional steps to go from that thing you just estimated to B, which is the thing of interest, to decide what your parent relationships are like in the DAG. So basically, this kind of ICA-based procedure will proceed by estimating W hat and then using kind of like looking at various permutations of that estimated matrix and normalizing the results and trying to say that the really small entries of that matrix are zero, right? So there's going to be some sort of thresholding thing because you'll never estimate real direct exact zeros. So you're going to have to prune the coefficients close to zero and then sort of work backwards to a B hat. And this is ICA procedures are like a huge area of signal processing and engineering. The kind of if you're not familiar with ICA, the typical, the kind of slogan by which it's often described is solving this cocktail party problem. So like imagining a room with people in a party where people are close to possibly different microphones that are listening to conversations in the room, and the microphones linearly mix conversations based on the distance from different people, and sort of unmixing those independent sources of variation is what ICA is kind of all about. And there's a huge literature and like fast algorithms for solving that problem. How do you do it if you have latent variables? Well, I think in this case, you have this setting where you have more sources than microphones. So you're sort of imagining that there's additional errors, which kind of represent your latent variables, that are these things together are mutually independent, but they may affect U may affect multiple of the X's, for example. So the way this is done is by doing a kind of overcomplete independent components analysis. It's described in this paper in the footnote. So with two variables and allowing for an unmeasured variable u, it'll kind of look like you have this asymmetric coefficient matrix and this column matrix of larger dimension than your observed data. And in that case, the way that it kind of, at least the kind of classic version, proceeds by using a mixture of Gaussians approximation. So it will, so if you represent each error as each non-Gaussian error as a mixture of Gaussians, a weighted mixture of Gaussians, you can write down what the likelihood looks like given the whole parameter set. And then under some assumptions, you can maximize that likelihood, estimate those parameters using a kind of EM approach. And then you're going to have to do, again, this kind of permutation issue and shrinking small coefficients to 0 and so forth. That will, in the end, where the ultimate goal is to recover the elements of this mixture matrix. Okay. Yes.
Do you need to know anything about epsilon, or it could be like anything? Like if there is some gap, maybe some gap that's that.
So for the identifiability result, again, the epsilons and u's have to be non-Gaussian, or at least
That's it. Like,
at most one of them can be Gaussian.
yeah.
It's positive.
It's positive. Frederick says there also be positive, but I don't remember. Okay. But also it's worth mentioning in practice, at least using this kind of mixture of Gaussian approach, how non-Gaussian the errors is makes a big difference too, right? Like if they're too close to Gaussian, you're going to do poorly because you're not identifiable. If they're too far away from Gaussians, then they're going to be poorly approximated by a mixture of Gaussians for some finite number of mixtures. And so there's a kind of trade-off between how non-Gaussian things will be in order for this particular estimation procedure to perform well. And that, I mean, that's actually, I think that there's open questions and results that one could try and prove about, like the degree of non-Gaussianity and how well that lets you recover the LIGAM model, and even in this linear case. And it's also worth mentioning that in the case, even though like a major benefit or a major, I don't know, pro of the LIGAM approach in the DAG setting is the fact that you can recover a unique DAG. That part's not really true once you start allowing for latent variables, because there'll be multiply observationally equivalent like latent variable models with different coefficients that are consistent with your data. And so in the case of latent variable LIGAM, you're actually going to return a kind of equivalence class of DAGs, but it's not necessarily an equivalence class in the same sense that a CP DAG works. Okay, so I'm not going to go too much deeper into the linear non-Gaussian stuff, but there is this existing literature. A major pro is this ability to identify at least sometimes a unique DAG or a relatively small equivalence class in the case of latent variable models. The cons, I would say, is that firstly, on the side of like assumptions, there's there's strong assumptions. Even with allowing for non-Gaussianity, the linearity assumption is quite strong. The statistical or asymptotic properties of these ICA-based algorithms are not really clear in a lot of cases. In particular, like results about how far away you are from the correct solution, I think will depend on a lot of things, including something about the degree of non-Gaussianity. If errors are either too close to Gaussian or too non-Gaussian, it's probably not going to perform well. And in practice, it often requires large sample sizes and relatively small dimensions. Frederick.
Thomas, do you want to say something?
Yes, sorry, I just wanted to add a little footnote here, which is that there is some work, it's very recent, so it's just within the last, it was published in 2020, but there's a paper by Wang and Matthias Berton on high-dimensional causal discovery under Nongaussianity in Biometrica, and that paper does present statistical guarantees, and it also recovers a DAG with bidirected edges. So in a certain sense, it does address some of the gaps that you were just highlighting, which I think were gaps until very recently. But yeah.
And then one other question is there no assumption of faithfulness with LIGAM, just the assumption about the functional form?
Good question, kind of tricky. So faithfulness is often not mentioned explicitly in the literature on LIGAM models, but there is a kind of faithfulness that ends up being assumed in the sense that certain faithfulness violations will mess up the algorithm. So there's a recent paper. There's a recent paper by Konstantin Jenin, and I think they talk about this, some uniform consistency result for linear models. Sort of, I guess the summary point is that yes and no. There's like faithfulness does not play quite as central a role in the theoretical results related to linear models, but also violations of faithfulness in some cases will mess up these algorithms and lead them to perform poorly. So there's like a kind of sneaked in faithfulness, I would say, that makes an appearance.
Elaborate a little bit about the dimension thing. What is the dimension here? Is that
P is the number of variables.
just the number of variables?
So I'm just making a kind of like empirical, practical observation that computationally it's difficult and accuracy-wise it's not great once you let P be quite large. So if I'm doing it with like.
And in what space are the variables themselves?
The x's themselves are here continuous variables that can follow any distribution except for Gaussian in a sense, right? So
But are they on the real line or?
yes, on the real line. So for a linear model, it's going to
So
be.
it's not the dimension of each variable.
Yeah, P is just the number of variables. That's what I mean by dimension. Yeah.
How does the scale?
I don't know a theoretical result of that form. I'm making a purely like empirical observation about it being computationally difficult. Yeah.
So with the linearity assumption being strong, I would guess that what you could do is you could define like tummy variables where you raise the variables that you have to higher powers, and now you could possibly deal with that. You could use kernel methods. What are the reasons that like those things would like break and not work here?
The question is about sort of trying to weaken the linearity assumption by, say, allowing for like polynomials in your variables or something like that. So you can go in that direction. It becomes a bit complicated because now, so like say I just did that and I said for every x, let me also add x squared and assume that it's linear in that kind of quadratic thing. Now there's no longer a single coefficient that corresponds to the edge being present or absent. Right, so like the nice thing about linear models is that if b, going back to here, like if bij is not equal to 0, that's like means that there's an edge there. Now if I start thinking about like polynomials in x, I have to make some decision about how to treat that, like how to do the correspondence between this like nonlinear function or like a set of coefficients representing this nonlinear function and the DAG itself. I don't think it's impossible, but it just like adds for a layer of complexity there. And these results that I've talked about so far also, like the linearity in X is crucial for using this ICA-based stuff. There is nonlinear ICA work that that has been leveraged to do this in a kind of nonlinear setting, but still using the ICA approach. But it's like a little bit different, and I won't talk about it here. And then instead, rather, I was going to talk a little bit about a kind of weakening of the linear non-Gaussian acyclic model and thinking about these additive models, which is kind of like another, what you might think is like a natural second step. But I think before I get into that, I think there's another question here.
So
Maybe I'm not the fan of LIGAM, okay, maybe it's my issue, but what I'm trying a little bit to understand intuitively, what I got is that Gaussian, the lack of Gaussianity would offer me enough asymmetry in order to find out a unique DAG. But that's does not work in my mind with the generality that we have expressed the non-Gaussianity. Because, for example, if I put Laplace distribution that is non-Gaussian, but it has like all the similar properties that someone can think like Gaussian, it seems that it will work. So what I am losing intuitively,
What will work?
the results about non-Gaussianity would play if I used Laplace distribution. And Laplace distribution seems to behave isoperimetrically. It's so nice like a distribution in comparison with.
But it has higher order moments.
Yeah, so like you can test, in some sense, you can test whether you're in a Gaussian or Laplacian setting and looking at those higher limits, right? And so the ICA kind of based procedures, which exploit non-Gaussianity to do this like mutual information stuff, they'll be different whether it's Gaussian or Laplace.
We will discuss it offline. I think it is clear.
Okay. Is there another question? Yes.
It's more of a practical question. So let's say I have a data set, and then I know all these methods, and then I run each of these on the data set, and then I get a different graph for these methods. So is there any ways that I can verify which one works better for my data set particularly? Or how do I know which one is good?
Yeah. So the question, to repeat for folks on Zoom, is if I have all these different methods and I run each one on a particular data set, how do I know which one is the best or most appropriate? There's no easy answer to that question. It depends also what you know about the truth. So in a simulation setting, when I know what the true structure is, because I've simulated it, I can straightforwardly compare which method gets me closer to the truth, right? In terms of structural Hamming distance or false positives or precision and recall or whatever it is. But in a lot of real applications, the reason you're doing causal discovery is because you don't know the truth. So there's not going to be, unless you can go ahead and like validate something about the graph you learned by doing, say, experiments, then there's not necessarily going to be a straightforward way to determine whether you are closer to the truth with one graph or another. I mean, you can do certain things like evaluate, like at least for certain classes of models, you can evaluate the fit of those models and see which one fits better by some metric. But there's no easy way to compare if you're doing better in one versus the other, unless you know something substantive about the true model.
Do you think like the stability of the edges would play a role in here? Let's say I divide the data set into like 100 times and then run it in.
Yeah, so the question is about stability of edges, and there are definitely papers that take that route, that sort of do subsampling and see how often a particular edge appears or doesn't appear, and you can come up with different evaluation methods for deciding like how confident you are in a particular edge, and that is one route to go down. So if I can, what time are we going to until 4? I mean 5? 4:30. 4:30. Okay, so I'm going to speed through this last little bit. So there's this other kind of semi-parametric work that instead of assuming linear non-Gaussian stuff, goes in the direction of additive noise models with nonlinear functions. So this is one where the epsilon is additive with respect to f of the parents. Somewhat surprisingly, if you assume Gaussian noise here, but nonlinear functions, so as long as there's some nonlinearity, you can also that's sufficient to identify the causal structure uniquely. But from the perspective of this lecture, which is kind of focused on variables that are amenable to unmeasured confounding and latent and hidden structure, a problem with the additive noise model setting is that this class is not closed under marginalization. So if I think about a DAG over X and L satisfying the A&M, the additive noise model, and then I marginalize over the L and just think about the induced structural equation model on the X's, that's no longer guaranteed to be in this additive noise class. So it's not really one that's easy or amenable to kind of a marginal latent variable setting. There's a kind of iteration on that that tries to relax things in even further. What's called the post-nonlinear causal model, which basically takes an additive noise model and then runs it through an additional nonlinear but invertible function. And so there's some results that under certain kind of technical conditions, by the way, some of those technical conditions kind of do resemble faithfulness in a more obvious sense because they rule out certain kinds of cancellations. Then you can show that there's a asymmetry induced on the joint distribution and that those directions can be distinguished from data. To end this little point, all of these kind of semi-parametric methods impose some assumptions or restrictions on the structural equations, derive some sort of asymmetry on the observed data distribution, and then check if the data exhibits the supposed asymmetry to try and infer backwards. I think there's a lot of open questions about the properties of such methods, and they can be computationally quite difficult. But one kind of nice thing is combining them with the existing methods. So there are times in which people have run, say, PC or GES or something similar, and then reduced the size of the equivalence class by additionally imposing one of these additive noise model type things or LIGAM model type things to get more informative output, so long as those additional structural conditions are met. So, and there are also new methods in this kind of space that are being developed all the time. I want to say a little bit about a different paradigm for causal discovery, which may be of particular interest to people here at Simons, because it draws on kind of more cutting edge stuff in optimization literature. So there's a recent set of proposals which combine a kind of score-based selection with ideas from continuous optimization, and often in practice parametric or semi-parametric assumptions. For example, if you say assume that the true data generating process is some sort of structural equation model, say like a linear structural equation model or whatever it might be, with some set of parameters theta, and let G of theta denote the corresponding graph that basically counts the non-zero entries in your parameter matrix, and use this kind of boldface G to denote a space of possible graphs that you might want to search over. For example, the space of all DAGs over some variables X, or the space of all MAGs or PAGs over variables X. And then let a score, and then define a score function kind of similar to BIC that maps some parameter vector estimated for a graph to higher or lower numbers, depending on whether it's a better fit. Then the kind of differentiable approach recasts the discrete search over possible graphs into a continuous search over parameter values by basically saying, I want to find a value of theta that minimizes some score such that the implied graph G for those thetas is in the class that I'm willing to consider, for example, the class of DAGs. And if you can find a function of theta that is 0 if and only if G is in that class, then now this becomes a continuous constrained optimization problem. So the key, there's a bunch of moving parts here, of course, but say once you define a score and a model class, the sort of key challenge is like a function of theta that is continuous and differentiable, such that 0 of that function is an indicator that you're in the right class. For example, the class of directed acyclic graphs. So the original version of this algorithm called NoTiers considers linear structural equation models. So the thetas are the linear coefficients. And they show that the induced graph is acyclic. They're interested in directed acyclic graphs if and only if this particular h evaluates to 0. So this is something that looks like the trace of the matrix exponential of theta times theta, where this is the dot is the Hadamard product, the element-wise product of the two matrices. So that's a function which takes the theta matrix, multiplies it by another theta matrix, takes the exponential and takes the trace, and then subtracts off the number of variables p. And so that quantity will vanish if there are no cycles in the graph. Question over?
Yeah, you had a statement that said you need to assume that it's actually the true theta exists in this class. Does it need to be like a true theta, or is there a notion of like in statistics of like best in class? So like the closest with whatever your loss is that your score function is defined as.
I think you probably could formulate it that way. You just won't have the kind of consistency result. I guess maybe I'm a little biased in the sense that I like consistency results, but yeah, you can probably formulate this as just like the one that minimizes some loss. Yeah. So in this particular case, to summarize it quickly, the author is sort of formulating this search problem as a continuous optimization problem. So they have this constraint that you can evaluate and solve, you can take derivatives of, and so you can use kind of state-of-the-art constrained optimization techniques to try and solve this problem in a kind of continuous way. Notice this assumes linear models, right? So you have to have some parameter vector that basically defines the DAG for you. And it's not always so straightforward to figure out how to relax that because of problems kind of like the ones I mentioned earlier. But it is a kind of nice or interesting formulation because you can now exploit a lot of existing stuff from the optimization literature to do this well. So in practice, people have used mostly the augmented Lagrangian approach. And in another paper, this has been extended to mixed graphs. So ADMGs of different classes, in particular MAGs, as well as other kinds of ADMGs that I'll mention in a second. Again, assuming a linear structural equation model, except now I have both coefficients and covariances between my errors to represent that unmeasured confounding. And so now if I define my space G to be the space of ancestral graphs, you can show that I can define this H function, which again is a continuous and differentiable function of a bunch of matrix parameters that is 0 if and only if the graph is ancestral. So the first part of it is basically just acyclicity. And then the second part of it counts the number of ancestrality violations. So if I define this kind of thing, I can do the same procedure, try and minimize some sort of score metric while satisfying this constraint on the parameters. And in the papers that I've seen, the kind of approach has been mostly to minimize the score using this kind of augmented Lagrange multiplier approach, solving the dual equation. And there's like a million things probably to be said about the stability and convergence properties of different optimization schemes here, but this is not something I'm personally very knowledgeable about, so I won't say more about it. There is a recent paper that compares a few different, or mostly theoretically compares a few different approaches to solving this optimization problem, and that might be of interest to folks. And then, oh yeah, and these are a couple of references. That's in terms of the scores that people use, the approach proposed by Zhang et al. Used a kind of L1 penalized likelihood score for DAGs, which I don't think is really consistent in their setting. In another paper by Bhattacharya and company, and full disclosure, I was a co-author on that paper, uses a different score that's an approximation to the BIC score. So that involves basically fitting likelihoods for ADMGs and then penalizing them somehow and calculating the derivative of that H function, for which we use this procedure that Thomas Richardson alluded to earlier about calculating maximum likelihood estimates for MAGs. And another kind of caveat that is worth emphasizing is that these procedures are kind of blind to equivalence class considerations. The approach so far has been to sort of hope you achieve a global optimum And then that will be one DAG or one ADMG in the equivalence class, and then transform it to a representation of the equivalence class, like a CP DAG or a PAG. And that is one way to go. There are issues with local optima in this case. And it's also harder if you try and extend this. So in the paper that I was somewhat involved in, we tried to extend this to more general classes of ADMGs besides MAGs. But the issue is that there's a lot of unanswered questions about Markov equivalence in that setting. So there's a lot that's really kind of unclear about how to do that properly. I'll skip this little bit. I wanted to mention really quickly a bit about another related approach that's kind of also optimization based in some sense. This permutation based approach to causal discovery, which formulates a score maximization problem over permutations of the vertices in a graph. So specified kind of abstractly, if you think about some space of possible permutations of the vertices in a graph, and the DAG or ADMG or whatever that those permutations induce, you can try and search over possible permutations, and for each permutation, calculate some score, try and minimize that score, or in this case, maximize. So permutation is like just thinking of the vertices as like an ordered, like a list of numbers, ordering them in some way such that the order reflects parent-child relationships in the graph as a total order, or a partial order if you're just thinking about ancestrality relationships. So you can define, so work by Carolyn Uhler and her collaborators defines a kind of score that's based on the sparsity of the resulting graph, and searches for permutations that minimize, or I guess maximize that score, phrased this way. This is kind of, I would say, on the surface, it's like kind of a score-based approach, but in reality, it might be better thought of as a hybrid approach because it involves maximizing some sort of score, but it also in practice involves testing a bunch of independence constraints. So you have to look for permutations that are consistent with the data in some sense. So they will test. So here I'm using kind of abstractly like the set of independence constraints implied by a graph. But in practice, you need to test those conditional independence constraints to determine whether your permutation is a candidate for a possible graph or not. So they do this in a couple of different papers, including one approach that focuses on causal orderings corresponding to DAGs, and then more recently, an approach that looks at partial orders, which corresponds to ancestral graphs or MAGs. So there's a lot of interesting problems and questions that kind of flow from this approach. And then I have a couple slides at the end that just a non-exhaustive list of different kinds of algorithms in the space of causal discovery that are color-coded by my kind of personal color coding scheme. So we have approaches that learn DAGs and CP DAGs. We have approaches that learn MAGs or PAGs or ADMGs of some sort. And we have approaches that learn cyclic graphs that I haven't had time to talk about today. And in each of these categories, you have things that are kind of constraint-based, like PC and FCI, and CCD, which is cyclic causal discovery. You have approaches that are score-based, like the GES, or these two algorithms I just described, the sparsest permutation algorithms, as well as stuff based on max-min hill climbing. You have approaches based on these semi-parametric assumptions we just discussed, including ICA lingam, but sort of other lingam-related variables. And there's a version of lingam that's for cyclic models, that's just called ling. And then we have stuff that doesn't really fit in super neatly into any of these categories, like methods based on SAT solvers and these differential causal discovery approaches. Here's a kind of partial list also of software packages that are available for structure learning in R, in Python, and in Java, MATLAB, and so forth. And finally, I'll conclude with just a couple of open problems, I guess, to stimulate discussions here at Simons, including, I think most of these I've kind of mentioned along the way. Better general purpose non-parametric conditional independence tests, I think, are super helpful and helpful for making algorithms, especially like PC and FCI, but also score-based stuff more flexible in non-parametric settings. There's a lot of room. I was asked earlier about greedy score-based methods for MAGs and PAGs. And so there's a lot of room for consistent, scalable, non-parametric and more algorithms for learning MAGs and PAGs or other classes of ADMGs. There's kind of theoretical questions that might help in the search for general ADMGs about characterizing Markov equivalents for those kinds of graphs. Better understanding of methods for learning graphs that combine confounding and cycles, I think are really interesting. So these would be directed mixed graphs without the acyclicity bit. There are open questions about consistency results that weaken the strong faithfulness assumption. And then there is the kind of broad question of statistically speaking, how to do valid post-selection inference. So given that you've selected a model and you might want to use the same data to then subsequently estimate some sort of causal effect or some interventional distribution, treating that model as if it were known. If you do that in a kind of naive way, your quantification of uncertainty will not be valid. Your confidence intervals will not have the correct coverage. And so there's like a large literature on post-selection inference in other branches of statistics, like in linear model selection. And I think that there's kind of a lot of open questions for how to do that properly in this space of the kind of discrete graph-based model selection that we do when we do causal discovery. So I'll end with that, and I'm happy to answer questions and stick around if people want to talk. Thanks for listening.
We can do questions afterwards. Let me just say, because we're out of time for tomorrow, let me repeat what I said before. Thomas will be doing this online. He'll be on screen here. We'll have microphones for questions from the room. Obviously, you can do this from home. If you are at home, then unless you are a panelist or a member for the program for the whole term, you will only be able to ask questions. Actually say something, then you would better come into the room. I will be here. It would be great to not be the only one here. It's nice to not have to drink the coffee on my own. But I completely understand if you want to do it from home tomorrow. Other than that, thank you very much, Dan, and hopefully I'll see many of you tomorrow, if not here, then online.
Will the slides be made available?
Yeah, they are available. So the slides are on my website under the teaching tab, and I think Frederick sent them around on the Zoom. Yeah, so one of those places.
I have a question.